Seismology is the scientific study of earthquakes and the propagation of elastic waves through the Earth or through other planet-like bodies. The field also includes studies of earthquake environmental effects, such as tsunamis, as well as diverse seismic sources such as volcanic, tectonic, oceanic, atmospheric, and artificial processes. A related field that uses geology to infer information regarding past earthquakes is paleoseismology. A recording of Earth motion as a function of time is called a seismogram. A seismologist is a scientist who does research in seismology. History. Scholarly interest in earthquakes can be traced back to antiquity. Early speculations on the natural causes of earthquakes were included in the writings of Thales of Miletus, Anaximenes of Miletus, Aristotle and Zhang Heng. In 132 CE, Zhang Heng of China's Han Dynasty designed the first known seismoscope. In 1664, Athanasius Kircher argued that earthquakes were caused by the movement of fire within a system of channels inside the Earth. In 1703, Martin Lister and Nicholas Lemery proposed that earthquakes were caused by chemical explosions within the Earth. The Lisbon Earthquake of 1755, coinciding with the general flowering of science in Europe, set in motion intensified scientific attempts to understand the behavior and causation of earthquakes. The earliest responses include work by John Bevis and John Mitchell. Mitchell determined that earthquakes originate within the Earth and were waves of movement caused by shifting masses of rock miles below the surface. From 1857, Robert Mallet laid the foundation of instrumental seismology and carried out seismological experiments using explosives. In 1897, Emil Wickert's theoretical calculations led him to conclude that the Earth's interior consists of a mantle of silicates, surrounding a core of iron. In 1906, Richard Dixon Oldham identified the separate arrival of P waves, S waves and surface waves on seismograms and found the first clear evidence that the Earth has a central core. In 1910, after studying the 1906 San Francisco earthquake, Harry Fielding Reid put forward the elastic rebound theory, which remains the foundation for modern tectonic studies. The development of this theory depended on the considerable progress of earlier independent streams of work on the behavior of elastic materials and in mathematics. In 1926, Harold Jeffreys was the first to claim, based on his study of earthquake waves, that below the crust, the core of the Earth is liquid. In 1937, Inge Lehmann determined that within the Earth's liquid outer core there is a solid inner core. By the 1960s, Earth science had developed to the point where a comprehensive theory of the causation of seismic events had come together in the now well-established theory of plate tectonics. Types of seismic wave. Seismic waves are elastic waves that propagate in solid or fluid materials. They can be divided into body waves that travel through the interior of the materials, surface waves that travel along surfaces or interfaces between materials, and normal modes, a form of standing wave. Body waves. There are two types of body waves, P waves and S waves. Pressure waves or primary waves are longitudinal waves that involve compression and rarefaction in the direction that the wave is traveling. P waves are the fastest waves in solids and are therefore the first waves to appear on a seismogram. S waves, also called shear or secondary waves, are transverse waves that involve perpendicular motion to the direction of propagation. S waves are slower than P waves. Therefore, they appear later than P waves on a seismogram. Fluids cannot support this perpendicular motion, or shear, so S waves only travel in solids. P waves travel in both solids and fluids. Surface waves. The two primary types of surface waves are the Rayleigh waves, which has some compressional motion, and the Love wave, which does not. Rayleigh waves can be explained theoretically in terms of interacting P and S waves of vertical polarization that are required to satisfy the boundary conditions on the free surface. Love waves can exist in the presence of a subsurface layer, and they are formed by S waves of horizontal polarization only. Surface waves travel more slowly than P waves and S waves, however. Because they are guided by the surface of the Earth, they can be much larger in amplitude than body waves, and can be the largest signals seen in earthquake seismograms. They are particularly strongly excited when their source is close to the surface of the Earth, as in a shallow earthquake or explosion. Normal modes, both body and surface waves, are traveling waves. However, large earthquakes can also make the Earth ring, like a bell. This ringing is a mixture of normal modes with discrete frequencies and periods of an hour or shorter. Motion caused by a large earthquake can be observed for up to a month after the event. The first observations of normal modes were made in the 1960s as the advent of higher fidelity instruments coincided with two of the largest earthquakes of the 20th century, the 1960 Valdivia earthquake and the 1964 Alaska earthquake. Since then, the normal modes of the Earth have given us some of the strongest constraints on the deep structure of the Earth. Earthquakes. One of the first attempts at the scientific study of earthquakes followed the 1755 Lisbon earthquake. Other notable earthquakes that spurred major advancements in the science of seismology include the 1857 Basilicata earthquake, 1906 San Francisco earthquake, the 1964 Alaska earthquake, the 2004 Sumatra-Andaman earthquake, and the 2011 Great East Japan earthquake. Controlled seismic sources. Seismic waves produced by explosions or vibrating, controlled sources are one of the primary methods of underground exploration in geophysics. Controlled source seismology has been used to map salt domes, anticlines and other geologic traps in petroleum-bearing rocks, faults, rock types, and long-buried giant meteor craters. For example, the Chicxulub crater, which was caused by an impact that has been implicated in the extinction of the dinosaurs, was localized to Central America by analyzing ejecta in the Cretaceous-Paleogene boundary, and then physically proven to exist using seismic maps from oil exploration. Detection of seismic waves. Seismometers are sensors that sense and record the motion of the Earth arising from elastic waves. Seismometers may be deployed at the Earth's surface, in shallow vaults, in boreholes, or underwater. A complete instrument package that records seismic signals is called a seismograph. Networks of seismographs continuously record ground motions around the world to facilitate the monitoring and analysis of global earthquakes and other sources of seismic activity. Rapid location of earthquakes makes tsunami warnings possible because seismic waves travel considerably faster than tsunami waves. Seismometers also record signals from non-earthquake sources ranging from explosions, to local noise from wind or anthropogenic activities, to incessant signals generated at the ocean floor and coasts induced by ocean waves, to cryospheric events associated with large icebergs and glaciers. Above-ocean meteor strikes with energies as high as 4.2 times 1013 J have been recorded by seismographs, as have a number of industrial accidents and terrorist bombs and events. A major long-term motivation for the global seismographic monitoring has been for the detection and study of nuclear testing, mapping the Earth's interior. Because seismic waves commonly propagate efficiently as they interact with the internal structure of the Earth, they provide high-resolution, non-invasive methods for studying the planet's interior. One of the earliest important discoveries was that the outer core of the Earth is liquid. Since S waves do not pass through liquids, the liquid core causes a shadow on the side of the planet opposite of the earthquake where no direct S waves are observed. In addition, P waves travel much slower through the outer core than the mantle. Processing readings from many seismometers using seismic tomography, seismologists have mapped the mantle of the Earth to a resolution of several hundred kilometers. This has enabled scientists to identify convection cells and other large-scale features such as ultra-low velocity zones near the core mantle boundary. Seismology and society. Earthquake prediction, forecasting a probable timing, location, magnitude and other important features of a forthcoming seismic event is called earthquake prediction. Most seismologists do not believe that a system to provide timely warnings for individual earthquakes has yet been developed, and many believe that such a system would be unlikely to give useful warning of impending seismic events. However, more general forecasts routinely predict seismic hazard. Such forecasts estimate the probability of an earthquake of a particular size affecting a particular location within a particular time span, and they are routinely used in earthquake engineering. Public controversy over earthquake prediction erupted after Italian authorities indicted 6 seismologists and 1 government official for manslaughter in connection with a magnitude 6.3 earthquake in L'Aquila, Italy on April 5, 2009. The indictment has been widely perceived as an indictment for failing to predict the earthquake and has drawn condemnation from the American Association for the Advancement of Science and the American Geophysical Union. The indictment claims that, at a special meeting in L'Aquila the week before the earthquake occurred, scientists and officials were more interested in pacifying the population than providing adequate information about earthquake risk and preparedness. Engineering, seismology. Engineering seismology is the study and application of seismology for engineering purposes. It generally applied to the branch of seismology that deals with the assessment of the seismic hazard of a site or region for the purposes of earthquake engineering. It is, therefore, a link between earth science and civil engineering. There are 2 principal components of engineering seismology. Firstly, studying earthquake history and tectonics to assess the earthquakes that could occur in a region and the characteristics and frequency of occurrence. Secondly, studying strong ground motions generated by earthquakes to assess the expected shaking from future earthquakes with similar characteristics. These strong ground motions could either be observations from accelerometers or seismometers, or those simulated by computers using various techniques, tools. Seismological instruments can generate large amounts of data. Systems for processing such data include CUSP, Radixpro seismic software, Seismograph. Notable seismologists: Aki, Kaiti, Donnell, Anderson, Bolt, Bruce, Klebout, John, Javonsky, Adam Marion, Ewing, Morris, Galatsina, Boris Borisovich, Gambitsev, Grigory A., Gutenberg, Benno, Huff, Susan, Jeffries, Harold, Jones, Lucy, Kanamori, Hairu, Kylais Boric, Vladimir, Nopov, Leon, Lehman, Inga, Mallet, Robert, Mercalli, Giuseppe, Milne, John, Mohorovičić, Andrea, Oldham, Richard Dixon, Fusaki Chiomori, Sebastião de Mello, Marquis of Pombal, Press, Frank, Richards, Paul G. Richter, Charles Francis, Sekia, Saket, Shie, Kerry, Paul G. Silver, Tucker, Brian, Vidal, John, Wen, Liangsing, Winthrop, John, Zhang Heng,